Somewhere out in the galaxy, or so we have always believed, there should be a star going slowly dark, swallowed by machinery, wrapped in the engineering of a civilization powerful enough to drink its entire sun. That is the picture we have carried for 60 years of what an advanced civilization looks like, and it is the thing we've been hunting for across thousands of stars. We have never found one. Not a single caged star, not one glowing engine, nothing but the same quiet dark. And a handful of recent studies now suggest a reason that should stop you cold, because it means we may have been looking for exactly the wrong thing. The most advanced civilizations may not blaze at all. They may be cold and silent and nearly invisible. So what did the Great Silence just reveal about the universe? Tonight, by the end, you will know exactly. Get cozy and settle in. Subscribe if you have not, and stick around, because to understand why the sky stays dark, you first have to see why the ladder we use to rank civilizations falls apart the moment you check it. Let's dive in. Part 1. The Oldest Silence. Go outside tonight, somewhere the city lights cannot reach, and look up. On a clear night, far from street lamps, you can see a few thousand stars with your naked eye. Every one of them is a sun. Behind the ones you can see are hundreds of billions more in our galaxy alone, and behind our galaxy are something like 2 trillion others, each with its own hundreds of billions of suns. The numbers stop meaning anything after a while. There are more stars in the observable universe than there are grains of sand on every beach and in every desert on Earth, and it is not close. And around a great many of those stars we now know there are planets, rocky ones, warm ones, worlds with oceans maybe, and skies and slow afternoons. So here is a simple question, and it has been quietly breaking the minds of very smart people for 75 years. If the universe is this big and this old and this full of places where life could get started, then where is everybody? That question has a name, and it comes from an actual afternoon. In the summer of 1950, a physicist named Enrico Fermi was walking to lunch with a few colleagues at Los Alamos in New Mexico. They were talking, half joking, about flying saucers and the odds of alien visitors, the way people do. And then the conversation moved on to other things. But somewhere in the middle of lunch, apparently out of nowhere after doing a little arithmetic in his head the way only a mind like his could, Fermi looked up and asked the question that would outlive him. Where is everybody? He was not being flippant. He had just run the numbers, roughly, the way you might estimate how many piano tuners live in a city, and the numbers screamed that the galaxy should be crowded. Let me show you the arithmetic he was doing, because once you feel it, the silence outside your window starts to feel very strange. Our galaxy is more than 13 billion years old. That is not a number you can picture, so try it this way. If the entire history of the galaxy were compressed into a single year, with the first stars igniting on New Year's Day, then all of recorded human history, every empire, every war, every song ever written, would fit into the last few seconds before midnight on December 31st. The galaxy has been here, turning slowly, making stars and planets, for an almost unimaginably long time before we showed up. Now suppose that somewhere in all that time, on just one of those hundreds of billions of worlds, life arose and became intelligent and built ships. Not fast ships, not magic ships, just ordinary, sluggish, realistic ships, crawling along at a small fraction of the speed of light, the kind we can already imagine building. Even at that crawl, a single determined civilization could spread from star to star, settling one system, waiting a while, then sending out the next wave, and in this slow, patient way, it could cross the entire galaxy in something like a few million to a few tens of millions of years. That sounds like forever. But against the age of the galaxy, it is nothing. It is the last few seconds before midnight. It means that if even one civilization had gotten a head start of a few million years, which is a rounding error in cosmic time, the galaxy should already be full of them. Their probes should be in our solar system. Their signals should be washing over the Earth. Their engineering should be lighting up the sky. And yet, when we look, we find nothing. We have been listening with radio telescopes since 1960. We have scanned the skies for the heat of alien machinery, for laser pulses, for the deliberate signature of someone saying we are here. We have looked at thousands of stars and now, with our newest instruments, at whole galaxies at once. And the answer, so far, every single time, is silence. Not a whisper. Not one confirmed signal. Not one built thing that we did not build ourselves. The sky is enormous and ancient, and as far as anyone has ever been able to tell, empty. It is worth pausing on just how carefully we have listened, because the silence is not for lack of trying. It began in earnest in the spring of 1960, when a young astronomer named Frank Drake pointed a radio dish in West Virginia at two nearby stars and waited to hear something, anything, that a mind might have sent. He heard nothing but the hiss of the universe, and in the decades since we have only strained harder. We have swept millions of radio channels at once. We have watched for the telltale flicker of a star being dimmed by something built. We have looked for pulses of laser light aimed our way, for the chemical fingerprints of industry in distant atmospheres, for the warm infrared exhaust that a civilization's machines would have to leak. Whole careers have been spent leaning toward the dark, hands cupped to the ear of the cosmos, and through all of it, across more than 60 years and countless stars, the cosmos has said nothing back. That is not the silence of a room no one has bothered to check. It is the silence of a room we have searched again and again with every tool we could build and still found empty. And this is what makes the paradox press on you if you let it. It is not just that we have not found anyone. It is that everything we know says we should have. The stars are old enough. The planets are common enough. The distances, enormous as they are crossable in the long ages the galaxy has already had. By every reasonable estimate, someone should have gotten here, or at least gotten a signal here, long before humans ever climbed down out of the trees. The galaxy has had more than enough time to fill with voices, and it is quiet. That gap between what should be and what is not a small thing you can shrug off. It is a hole in our understanding of the universe, and every honest attempt to fill it leads somewhere unsettling. There is a version of this argument that makes the silence even harder to explain away, and it is worth hearing because it closes off the easy escape routes. You might say, well, maybe travel between the stars is simply too hard, too slow, too expensive, and no one ever bothers. But a civilization does not need to send living beings anywhere. It only needs to send one machine. Imagine a probe clever enough to arrive at a distant star, gather raw material, and build 2 copies of itself, which then fly on to 2 more stars, where each builds 2 more, and so on. Even starting with a single such probe, and even crawling along at speeds we could imagine building today, this doubling wave would sweep across the entire galaxy in a handful of million years. One civilization, one machine, a few million years, and the galaxy has had billions of years for anyone to try it just once. So the silence is not merely the absence of visitors, it is the absence of their machines, their messages, their leftovers, their footprints of any kind, when even a single modestly ambitious civilization should have filled the galaxy with evidence long before humans existed. That is what makes the quiet so genuinely strange. It is not that contact is hard, it is that the galaxy should already be saturated, and it looks pristine. That gap between the crowded galaxy the arithmetic promises and the silent one we actually observe is what we call the Fermi paradox. And it is not a small puzzle you can wave away. It is one of the deepest and most uncomfortable questions in all of science, because every answer to it is disturbing in its own way. Maybe life is almost impossibly rare, and we are alone. Maybe civilizations always destroy themselves. Maybe everyone is out there but staying quiet on purpose, hiding from something. For 75 years we have argued over these answers, and each generation reaches for the tools and the fears of its own age to try to explain the quiet. Tonight, I want to tell you about a new answer. It arrived very recently, in a handful of research papers published in the last year, and it comes from a direction almost nobody was looking. Because these papers did not start by asking about aliens at all. They started by asking a much stranger question. They asked whether the ruler we have been using to measure alien civilizations, the famous scale that sorts them into types, has been broken this whole time, and when they checked, carefully, against 60 years of real data, they found that it was. The ruler was wrong, and fixing it changes the entire shape of the question. It changes what an advanced civilization even is. It changes what we should have been looking for, and it suggests, in a way that is genuinely hard to shake once you have seen it, that the reason we have never found anyone is not that the universe is empty. It is that we have been searching for exactly the wrong thing. The thumbnail on this video says 3 words, We were wrong. By the end of tonight, I want you to understand exactly what we were wrong about and why it might be the most important mistake our species has ever made about its own future. But to get there, we have to start with the ruler. We have to start with a Soviet astronomer, a very simple idea, and a number so large it does not fit inside the lifetime of the sun. Part 2. The ladder we built for the stars. To understand what these new studies overturned, you first have to understand the thing they took aim at, and it is one of the most beloved ideas in all of popular science. If you have ever watched a documentary about alien life, or read a science fiction novel with a truly advanced civilization in it, you have almost certainly met this idea already, even if you never heard its name. It goes back to 1964 and to a radio astronomer in the Soviet Union named Nikolai Kardashev. Kardashev was wrestling with a very practical version of Fermi's question. He was not asking in the abstract whether aliens exist. He was asking something an engineer could use. If a civilization out there were broadcasting, how powerful would its signal be? What should we actually point our telescopes at, and what should we expect to hear? And to answer that, he needed a way to rank civilizations, some universal measuring stick that would work no matter what the aliens looked like or what they believed or what strange things they wanted. He needed one number that captured how advanced a civilization is, and he made a brilliant, simple choice. He decided to rank civilizations by energy, by the total amount of power a civilization can harness and put to use. Think about why that is such a clean idea. Almost everything a society can do, it does with energy. Growing food, building cities, sending signals, launching ships, running machines, keeping warm, thinking. The more energy you command, the more you can do, full stop. Energy is the one currency that every civilization, anywhere in the universe, has to spend, whether it is made of people or machines or something we cannot imagine. So Kardashev took that currency and drew a ladder with it. 3 rungs. The first rung he called a Type 1 civilization, a planetary civilization. This is a species that has learned to harness all the energy available to it on its homeworld. Every drop of sunlight falling on the planet, every wind, every wave, the heat of the planet's own core, all of it, captured and put to work. That is an enormous amount of power, something on the order of 10,000 trillion watts, a number we would write as a 1 followed by 16 zeros. A Type 1 civilization is the master of its own planet, in the most literal energy sense of the word. The second rung is where it gets dizzying. A Type 2 civilization, a stellar civilization, has outgrown its planet entirely and learned to harness the total energy output of its own star. Not the sunlight that happens to fall on one planet, but all of it. Every photon the star pours out in every direction, the entire fire hose of a sun's power. That is roughly 10 billion times more energy than a Type 1 commands. To capture that much, a civilization would have to build something almost beyond imagining, some enormous structure or swarm of collectors wrapped around its star, drinking in its light from every angle. This idea has a name too, the Dyson sphere, after the physicist Freeman Dyson who described it. Picture a star, and then picture it slowly disappearing behind a shell of machinery built by a civilization patient and powerful enough to take apart planets and rebuild them into a cocoon around the sun. That is a Type 2. Hold on to that image of the enclosed harvested star because it is going to matter enormously later. For 60 years, that glowing shell has been the picture of what a truly advanced civilization looks like. And then there is the third rung, the top of the ladder, a Type 3 civilization, a galactic civilization. This is a species that has spread across its entire galaxy and commands the energy of not one star, but hundreds of billions of them. The power of a whole galaxy, bent to a single civilization's will. The numbers here stop being numbers and start being something closer to poetry. It is a level of power we can name but not truly picture. That middle rung, the Type 2, deserves a second look because it is the one that captured our imaginations most completely, and it is the one this whole story eventually turns on. The idea of wrapping a star in machinery is not just a poetic flourish. It came from a real physicist, Freeman Dyson, who pointed out something almost obvious once you hear it. A star pours out its energy in every direction, and a planet catches only the tiniest sliver of that flood, a few billionths of the whole. Nearly all of a star's light simply escapes into empty space, wasted forever. So a civilization hungry enough for power would eventually stop catching the sliver and start catching the flood. It would take apart the useless planets of its system, the way you might dismantle an old barn for its lumber, and rebuild that material into an enormous cloud of collectors surrounding the star, drinking in its light from every angle at once. From the outside, you would watch the star slowly vanish, its visible light swallowed, and reappear only as a dull warmth, the heat of all that captured energy being used, and then inevitably thrown away. That warm glow, that leaked heat, became the thing we decided to hunt for. If you want to find a truly advanced civilization, the reasoning went, look for a star that has gone strangely dim and warm, a sun wrapped in the exhaust of its own harvesting. For 60 years that has been the picture of alien greatness, a caged star. Remember it. It is easy, listening to all this, to feel how seductive the ladder is. It takes the most unanswerable question in the universe. How advanced could a civilization become? And it turns it into a tidy sequence you can count on one hand. Planet, star, galaxy. 1, 2, 3. It gives our own future a direction and a shape, and it lets us place ourselves on the same scale as the gods we imagine out among the stars, just much, much lower down. There is real beauty in that. There is also, as we're about to see, a hidden flaw sitting right at the base of it, quietly waiting for someone to check the math. Now, where does that leave us? Where does humanity right now sit on Kardashev's ladder? And here is the humbling part. We are not even on the first rung. We do not yet command all the energy of our own planet. Not even close. Using a formula that the astronomer Carl Sagan later worked out to fill in the gaps between Kardashev's whole number types with a smooth scale, our current global energy use puts humanity at about 0.7. 0.7. We are a fraction of a Type 1, a planetary civilization still in its childhood, still burning things we dug out of the ground, still unable to manage the full energy budget of the single world we live on. We are, in the grand ranking of possible civilizations, just barely getting started. You can see why this scale caught fire in the popular imagination. It is so clean. A single number, running from a fraction up through 1 and 2 and 3 and beyond, that promises to sort any civilization anywhere in the cosmos onto one universal ladder. It turned the impossible question, how advanced is an alien civilization, into something that felt almost measurable, and it quietly shaped how our entire species pictures its own future. When you imagine humanity 1,000 years from now, or 10,000, you probably imagine us climbing this ladder, don't you? More energy, bigger engines, cities on other worlds, eventually maybe a sphere around the sun. When you imagine a superior alien civilization, you probably imagine it high on this ladder, blazing with harnessed starlight, a godlike engine burning brighter than anything we could build. For 60 years that was the picture. Advanced means powerful. Powerful means more energy. More energy means a bigger fire. It felt so obvious that almost no one thought to question it. And that is exactly the assumption that a researcher, in the last year, decided to actually test against the real world. He took Kardashev's beautiful, beloved, confident ladder, and he checked whether it holds up when you feed it 60 years of hard data. And it did not just wobble. It fell over completely. It produced a number so absurd that it tells you immediately that something at the very foundation of the ladder is wrong. Part 3. The number that broke the ladder. The trouble starts with a prediction Kardashev made about time. It is easy to overlook because it sounds so reasonable. He assumed that a civilization's energy use would grow at a steady, gentle rate, about 1% per year. 1%. That is a modest, believable number. Economies grow, populations grow, technology improves, and along the way we use a little more energy each year than the last. Compound that at 1%, year after year, century after century, and you can calculate how long it would take a civilization to climb the ladder. So Kardashev did. And from that 1% assumption, he worked out the timeline. Humanity, he calculated, would reach full Type 2 status, complete command of our star's energy, in about 3,200 years, and we would reach Type 3, galactic power, in roughly 5,800 years. For decades, those numbers got quoted in books and documentaries as if they were mile markers on a road we were actually driving. 3,000 years to a Dyson sphere. It sounded almost cozy, distant, but reachable, a destiny with a date on it. But in the last year, a researcher named Sebastian Gurevich did something that, astonishingly, almost no one had bothered to do in 60 years. He checked. He took Kardashev's assumption of steady 1% growth and he laid it against the real measured record of how much energy humanity has actually used, year by year, across the 6 decades since 1964. We have that data now. We did not, really, when Kardashev was writing. And when Gurevich compared the tidy 1% curve to what actually happened, the curve did not fit. It did not fit at all. For one thing, our real energy growth has run closer to 2% than 1%, faster than Kardashev guessed. But more importantly, it did not grow smoothly. Real energy use does not climb a clean, patient curve. It lurches, it surges and stalls and sometimes drops, knocked around by what statisticians call black swan events, sudden shocks nobody saw coming. Think of the year the coronavirus pandemic began, when the whole world locked down at once and global energy use fell off a cliff in a way no gentle upward curve would ever predict. Reality is jagged. It does not honour the smooth assumptions of a formula written in 1964. And here is where it gets strange and then genuinely disturbing. Gurevich took the real data and tried to project it forward honestly, using a simple straight-line model instead of Kardashev's neat exponential. He asked, based on how we have actually grown, how long would it really take humanity to reach Type 2, to command the full energy of the Sun by this measure of raw watts? And the number that came out was not 3,200 years, it was 1.6 quadrillion years. Let me make sure that number lands, because it is the hinge this whole video turns on. A quadrillion is a 1 followed by 15 zeros, 1.6 quadrillion years. That is not merely longer than human history. It is not merely longer than the time since the dinosaurs, or since complex life began, or since the Earth itself formed. It is enormously, catastrophically longer than the future our own star even has to give. Our Sun has been burning for about 4.5 billion years, and it has roughly 5 billion years left before it swells into a red giant, boils the oceans, and very likely swallows the Earth entirely. 5 billion years. And this old ruler, taken at its word, says that humanity would need 300,000 times longer than that, more than a quadrillion years, just to climb to the second rung of the ladder. Sit with the weight of that for a moment. A ruler that predicts something can never happen, on a timescale longer than any star will ever shine on any planet, is not a ruler that is slightly off. It is a ruler that is measuring the wrong thing entirely. It helps to understand why the old prediction and the new one diverge so wildly, because the reason is a lesson about the nature of growth itself. Kardashev assumed steady, compounding, exponential growth, the kind where you multiply by a little more each year. An exponential growth is a powerful thing. Compound even a modest rate for long enough, and the numbers explode upward, which is exactly why his 3,000-year timeline felt so reachable. But exponential growth is also a fragile assumption. It requires that nothing ever interrupts the climb, that a civilization simply keeps multiplying its energy use, smoothly, century after century, without pause, without limit, without a single stumble. And real history does not work that way. Real growth is not a smooth exponential curve. It surges when times are good, and stalls when they are not. It hits walls and finds ways around them and hits new walls. When you stop assuming the fantasy of unbroken exponential growth and instead take the messy, jagged, straight-line trend that the real data actually shows, the projected climb to a Type 2 civilization stretches from a few thousand years to a number longer than the age of everything. The tidy exponential was doing an enormous amount of hidden work, and once you take it away and look at what has really happened, the ladder simply falls apart. And notice what this really means, because it is not that humanity is doomed to crawl for a quadrillion years. It is something stranger and more interesting. It means the question was wrong. A civilization does not become great by slowly, endlessly multiplying its raw power until it can wrap a star. That road, measured honestly, goes nowhere in any reasonable amount of time. If greatness were really about raw watts, then no civilization anywhere, including any of the ones that should have filled this galaxy long ago, would ever have reached the second rung, because the universe does not last long enough for that road to arrive anywhere. The very fact that the old ruler produces an impossible answer is a clue. It is the universe telling us that we have been measuring the wrong quantity all along. The scale that our whole species has used to imagine its future, the clean ladder in every documentary, the confident 3,000-year march to a Dyson sphere, produces, when you finally check it against reality, a prediction so absurd that the universe would end many times over before it came true. This is what the paper calls Kardashev's conundrum. The old way of ranking civilizations by simply counting up their watts quietly and completely breaks. And I want you to feel what that does, because it is more than a technical footnote. Most of us grew up with this ladder. We absorbed it from science shows and space books and late-night daydreams about the far future. It gave shape to our hopes. It told us that progress meant climbing, that to become great was to command more and more power, that somewhere out there the truly advanced beings were the ones with the biggest engines and the brightest fires. And now, when someone finally holds that ladder up to the light and checks its arithmetic, it collapses in his hands, spitting out a number longer than the life of the sun. There is a specific kind of vertigo in that. It is the feeling of a certainty you did not even know you were leaning on suddenly giving way beneath you. If the ruler is this wrong, then the confident picture we have all been carrying, the glowing Dyson sphere, the godlike engine, the advanced civilization as a bigger and bigger fire might be wrong too. Not slightly wrong, wrong at the root. And here is the thing about a mistake at the root. It does not just weaken one branch of what you believe, it reaches up through everything that grew out of it. For 60 years, an enormous amount of our thinking about alien life quietly rested on this one assumption, that advancement means more energy. It shaped where we pointed our telescopes, because we went looking for the waste heat of enormous engines. It shaped what we imagined a first encounter would be like, because we pictured beings of overwhelming power. It shaped the answers we gave to Fermi's question, because if advanced civilizations are supposed to blaze across the sky, then their absence demands a dramatic explanation, a great filter, a dark forest, a cosmic catastrophe. Pull out the assumption at the root, and every one of those branches has to be re-examined. Maybe we pointed the telescopes the wrong way. Maybe a first encounter would be with something quiet and small. Maybe the silence never needed a catastrophe to explain it at all. That is what it means for the thumbnail to say we were wrong. Not wrong about one detail, but wrong about the shape of the whole question, in a way that ripples outward and touches everything we thought we knew about who might be out there. This is the disorienting gift of a broken assumption. It is uncomfortable, because it takes away a certainty you were leaning on without even realizing it. But it is also a door, because the moment you see that the old ruler was measuring the wrong thing, you get to ask, for the first time in 60 years, what the right thing might be. And that question, once you follow it, leads somewhere genuinely new. And do not mistake this for a criticism of Kardashev himself. He was a brilliant man solving a real problem with the tools of his time, and in 1964, energy was a perfectly sensible thing to measure. In those years, human progress really did look like a story of raw power. We had just split the atom. We were building bigger rockets, bigger dams, bigger reactors, bigger everything. The future, seen from the middle of the 20th century, was a future of more, and energy was the obvious currency of more. Kardashev cannot be blamed for missing a revolution that had not happened yet, the revolution in computing and information that would only truly take off decades after he wrote. He measured the thing that mattered most in his moment. It is only now, with 60 years of hindsight and a world transformed by information technology, that we can see the thing he could not. The story of progress quietly stopped being about power and became about something else, and the ruler never got updated. That collapse is the first crack, and everything that follows tonight is the story of what pours through it once it opens. Because the reason the ladder breaks is not random. It is not that Kardashev was foolish. It is that he, and all of us after him, were measuring the one thing that turns out not to be the point. We were counting the size of the fire, and the size of the fire, it turns out, was never what made a civilization advanced at all. Part 4. What the ladder forgot. So why does the ladder break? Once you see the reason, it is almost embarrassingly simple, and you will never look at the idea of an advanced civilization the same way again. Kardashev's scale measures only one thing: quantity. How many watts a civilization pushes through its machines. That is it. It reads the power meter and nothing else. And a power meter, it turns out, is blind to the single most important thing about how a civilization uses its energy. It cannot see quality. It cannot see what the energy is actually for, or how much of it is simply thrown away as waste. Let me give you a picture that makes the flaw obvious. Imagine two civilizations on two different worlds, and imagine that they consume exactly the same colossal amount of power. On Kardashev's ladder, they get the same score. They sit on the same rung. But now look closer at what each one is doing with all that power. The first civilization is crude. It burns its energy in enormous wasteful engines that roar and glow and throw off almost all of their power as useless heat, accomplishing very little for all the fuel they consume. It is like a bonfire the size of a city that cooks one potato. The second civilization is something else entirely. It takes that same amount of power and channels nearly all of it into fantastically delicate, sophisticated work, into computation and learning and communication, into thinking, wasting almost nothing, throwing off barely a whisper of heat. Same watts, same rung on the ladder, and yet, by any meaning of the word advanced that actually matters, these two civilizations are not remotely alike. One is a brute, the other is a genius, and Kardashev's scale cannot tell them apart because it only ever looks at the size of the fire, never at what the fire is being used to do. That is the flaw. As Gurevich puts it, power measured in watts is dimensionally incomplete as a measure of how advanced a civilization is. It captures the quantity of energy, but not the quality of its use. You can watch this same principle play out in the history of our own species, if you know where to look. A steam engine from the 1700s and a modern power plant might both be described as burning fuel to do work, but the modern plant extracts several times more useful work from the same lump of coal, because engineers spent 2 centuries learning to waste less. An old light bulb turned almost all of its electricity into heat, and only a sliver into light, which is why it grew hot enough to burn your fingers, while a modern light-emitting diode turns most of the same electricity into light and stays cool. In every case, the story of progress is not that we started using more energy. It is that we learned to throw less of it away. The fire got cleaner, and if you tried to rank a steam engine against a modern plant, or an old bulb against a new one, purely by how many watts they consume, you would completely miss the thing that actually improved. You would be counting the fuel and ignoring the genius. That is precisely the mistake the Kardashev scale makes, only projected up to the scale of entire civilizations. Here is another way to feel it. Your brain runs on about 20 watts of power, roughly the same as a dim light bulb, and with those 20 watts it does something no machine on Earth can yet match, holding a lifetime of memory, recognizing a face in a crowd in an instant, dreaming, reasoning, loving. 20 watts. Now imagine ranking your mind against a roaring industrial furnace that consumes 1,000,000 times more power and produces nothing but heat. By the raw watts ruler, the furnace wins in a landslide. It is 1,000,000 times more powerful. And yet, which one would you call more advanced, the furnace or the mind? The question answers itself, and it exposes the whole flaw in one stroke. Advancement was never about how much energy you command. It was always about what you can do with it. It was always about the quality of the fire, not the size. And the more you think about it, the more you realize that quality might be the whole story. Because the real trajectory of any maturing civilization is probably not toward burning more and more. It is toward doing more and more with less, toward efficiency, toward wasting less of every joule. A grown-up civilization is not the one with the biggest bonfire. It is the one that has learned to accomplish miracles with a candle. And here is the beautiful part. This is not a brand new idea dreamed up last year. It is an old intuition, one that came from the very pioneers of the search for alien life, and it was quietly ignored for 50 years. Back in the 1970s, 2 of the great early thinkers about extraterrestrial intelligence, the Soviet astronomer Iosif Shklovsky and the American Carl Sagan, the same Sagan who gave us the smooth version of the Kardashev scale, wrote together about exactly this. They argued that a civilization's advancement cannot be measured by energy alone. It must also be measured by its mastery of information, not just how much power you can move, but how much complex, organized, meaningful knowledge you can create, store, and transmit with it. Sagan's instinct was that raw power is only half the story, and that the other half, information, might be the more important half by far, and if you take Sagan's idea seriously, it quietly rewrites what the whole ladder should measure. Under the old scale, you climb by capturing more energy, first your planets, then your stars, then your galaxies. But under an information scale, you climb by doing more with what you have, by packing more organized thought into every joule, by turning raw power into meaning with less and less waste. Those are 2 completely different pictures of what it means to rise. One is about reaching outward and grabbing more fuel, the other is about turning inward and getting better, and they predict wildly different futures. On the energy ladder, an advanced civilization sprawls across the sky. hungry, ever-expanding, grabbing stars. On the information ladder, an advanced civilization might barely grow at all in physical terms, might even shrink and cool and quiet down, while its inner life, its thought, its richness, explodes upward beyond anything we can imagine. Sagan saw that second picture 50 years ago. He just had no way to measure it, and so the field kept climbing the wrong ladder. For 50 years that idea drifted along as a kind of philosophical footnote, admired but unused, while the confident watt-counting version of the Kardashev scale got all the attention. It was easy to see why. Energy you can measure. You can point at a number and say, that civilization commands this many watts. But information, mastery, the quality of thought, how on earth do you put a number on that? How do you measure how good a civilization is at turning energy into organized intelligence? For half a century, nobody could. It stayed a lovely idea with no ruler behind it. And that is the gap these new papers finally close. They found a way, an almost absurd and completely unexpected way, to actually measure the thing Sagan pointed at. To put a hard number on how efficiently a civilization converts raw energy into pure information. And the measuring stick they reached for is so strange, so out of left field, that when I first tell you what it is, you are going to think I have wandered into the wrong video. But stay with me, because it is not what it sounds like, and it is one of the cleverest ideas I have come across in a long time. Part 5. The strangest yardstick in the world. Here is the problem Gurevich faced. He wanted to measure, across many years, how efficiently our civilization turns energy into computation. He wanted a single, honest, global number that tracked real thinking work being done, one that nobody could fake and anybody could check. And he found that number in just about the last place you would ever look for a statement about the destiny of intelligent life. He found it in a cryptocurrency network. Now, before you reach for the button, let me say this clearly. This is not a video about cryptocurrency. It is not an endorsement of anything. It is not about money. It is not about getting rich or the price of some coin. The point Gurevich is making has nothing to do with any of that. He needed a very specific kind of scientific measurement, and it just so happens that one particular network on Earth keeps the cleanest possible record of it, out in the open for anyone to audit. So let me explain what he actually did, because the logic is genuinely elegant. The Bitcoin network runs on something called a hash rate. You do not need to understand the cryptography to understand the idea. All the computers on that network are constantly performing an enormous number of calculations every second, grinding through cryptographic puzzles, and the hash rate is simply the total count of those calculations, worldwide, at any given moment. It is a measure of raw computational effort. And here is the crucial thing. That number is public. It is continuously published. It is auditable, and it is effectively impossible to fake, because the whole system is built on being able to verify it. It stretches back to 2009, when the network began. So whatever else you think about it, the Bitcoin hash rate is a uniquely honest, uniquely global logbook, running for more than a decade, of energy being converted into pure computation. It is the one number on Earth that records, in an unforgeable way, how much raw thinking work an entire planet's worth of specialized machines is doing. So Gurevich proposes a new unit. Take the total energy the whole world produces in a given year, divide it by the Bitcoin network's total hash rate that year. What you get is a number measured in joules per hash, the amount of energy it costs to perform a single unit of computation. He gives this unit a name, stitching together two of the people in this story. He calls it the Karnak, from Kardashev and from Nakamoto, the pseudonymous figure who created Bitcoin. And that unit, the Karnak, is a direct physical measurement of exactly the thing Carl Sagan cared about half a century ago. It measures how much energy a civilization has to burn to accomplish one piece of organized information work. It is, finally, a ruler for efficiency. And then Gurevich did the thing that makes this whole story detonate. He tracked that Karnak number across the real data, from 2009 all the way to 2024, 15 years, and he asked over that time how much did our civilization change? And the answer came back in two wildly different numbers, and the gap between them is the whole point. Over those 15 years, the total energy our civilization produces increased by only about a factor of 4. 4 times more raw power. That is the Kardashev number, the size of the fire, and it grew slowly, just as it always has. But the efficiency, the Karnak, the amount of computation we can wring out of each unit of energy, that number improved by roughly 14 orders of magnitude. 14 orders of magnitude. That is a 1 with 14 zeros after it. That is a factor of about 100 trillion. Let me put those two numbers side by side, because it is almost hard to believe they describe the same 15 years. Our raw power grew 4 times. Our efficiency at turning that power into organized thought grew 100 trillion times. Let those two numbers really sink in, because the gap between them is the entire thesis of this video in miniature. If you had been watching humanity through the old Kardashev lens, measuring only our raw power, you would have seen a civilization creeping upward, 4 times more energy across 15 years, plodding along towards some distant rung it would never reach. You would have concluded that we are barely moving, barely advancing at all. But that lens would have been blind to the real revolution, because in those exact same 15 years, by the measure that actually matters, we advanced 100 trillion-fold. The old ruler saw a snail, the new ruler saw an explosion, and that is precisely the mistake we may have been making about alien civilizations too. Looking through the wrong lens, we scan the sky and see nothing advancing, nothing blazing, nothing growing, and we conclude the universe is empty or asleep. But if the real action is in efficiency rather than in raw power, then a civilization could be racing forward at an unimaginable pace, advancing 100 trillion-fold, and remain completely invisible to a ruler that only knows how to count watts. We were measuring the snail and missing the explosion, both at home and across the stars. Why such an insane difference? Because the machines doing the computing were transformed. When the Bitcoin network began, it ran on ordinary general-purpose processors, the same kind of chip in a home computer, which are jacks of all trades and therefore wildly inefficient at any single specialized task. But within a few years, the network moved to a completely different kind of hardware. Chips called application-specific integrated circuits, machines etched to do one narrow calculation and absolutely nothing else, at blistering speed, wasting far less energy per operation. And that same leap has been quietly happening across all of computing, and in fact across all of history. It runs in a straight line from the ancient Antikythera mechanism, a 2,000-year-old set of bronze gears that could predict the positions of the sun and moon, through Charles Babbage's brass difference engine in the 1800s, all the way to the specialized silicon humming inside the phone in your hand. The whole arc of civilization, seen this way, is not the slow climb in raw watts that Kardashev tracked. It is a blistering, accelerating climb in how much thinking we can extract from every single joule. Let me put you inside that gap for a moment, because it is the real shape of progress, and almost nobody has ever seen it laid out this way. Imagine 2 machines, separated by 15 years. The first is an early mining rig from around 2009. It is just an ordinary desktop computer, sitting in somebody's bedroom, its fan whirring, its processor warm to the touch, chewing through cryptographic puzzles one clumsy step at a time, and throwing off most of the energy it draws as plain useless heat into the room. A lot of power goes in, a little bit of organized work comes out. It is a small fire doing a small job, and doing it badly. Now walk forward 15 years and stand in front of the second machine. It is a wall of those specialized chips, each one carved to do a single calculation and nothing else, running cool and fast and relentless, performing in a single heartbeat what that old desktop would have needed longer than a human lifetime to finish. Same task, same underlying laws of physics, and in the gap between those two machines sits 100 trillion-fold improvement in how much thought each joule of energy can buy. Stand there, between the warm, clumsy desktop and the cool, relentless wall, and you're looking at the true arc of an advancing civilization. Not bigger fires. Fires that waste less and less and less, creeping towards some ultimate floor where almost nothing is thrown away at all. I want to linger on why the Bitcoin hash rate works so well as a yardstick, because it is easy to hear cryptocurrency and stop listening, and the cleverness is really in the choice. Gurevich needed a measurement with 3 specific properties, and they are surprisingly hard to find altogether. He needed something global, so it captured a whole civilization's worth of computation, and not just one lab or one country. He needed something continuous and long-running, so he could track the trend across many years rather than guessing from snapshots. And above all, he needed something honest, a number nobody could quietly fudge or exaggerate, because the whole point was to measure real work actually done. Most measurements of computation fail at least one of these. Companies keep their efficiency numbers secret. Estimates of global computing power are cobbled together from guesses. But the hash rate of a public cryptographic network is, by its very design, none of those things. It is published continuously, verified by the entire network, effectively impossible to fake, and it reaches back more than a decade. Whatever you think of the coin, the network accidentally created the single cleanest public record of raw computation that has ever existed. Gurevich simply noticed that this messy, controversial thing had, buried inside it, exactly the honest yardstick that Sagan's 50-year-old idea had always lacked. And when you use that yardstick to look backward across all of history, not just the last 15 years, you see the same trend stretching into the distant past. The ancient Greeks built a device called the Antikythera mechanism, a hand-cranked box of bronze gears that could predict eclipses and the motions of the planets. It was, in its way, a computer, turning the muscle energy of a turning hand into astronomical information. Then came Charles Babbage, in the 1800s, with his difference engine, a tower of brass wheels meant to grind out mathematical tables by steam and by crank. Then vacuum tubes, then transistors, then the etched silicon in your pocket. At every step, the amount of computation you could extract from a given amount of energy leapt upward. The whole march of human technology, seen through this one lens, is a single unbroken story, thousands of years long, of learning to buy more and more thought with less and less energy. The Karnak unit simply makes that ancient story measurable for the first time and reveals that the real curve of civilization was never the slow one Kardashev drew. It was this one, steep and relentless, bending toward a floor. And that raises the question that the entire second half of this video is going to answer. If efficiency is the real measure of a civilization, and if the whole trajectory of progress is toward wasting less and less energy per thought, then there must be a flaw. There must be some ultimate limit set by physics itself, below which no computer, no brain, no mind of any kind anywhere in the universe can ever go. And it turns out there is. It has a name. And what happens when a civilization finally reaches it is the most surprising and unsettling part of this entire story. Part 6. The flaw beneath every thought. If efficiency is the real ladder, then somewhere at the bottom of that ladder there has to be a last rung, a hard physical flaw, a point past which you simply cannot get any more efficient no matter how clever you are because the laws of the universe forbid it. And there is such a flaw. It was discovered more than 60 years ago, and for most of that time almost nobody thought it would ever matter to anything real. It is called Landauer's limit, and to understand it, we have to talk for a moment about the strange, fundamental connection between information and heat. Back in 1961, a physicist named Rolf Landauer, working at IBM, asked a deceptively simple question. Does thinking cost energy? Not because our machines happen to be clumsy, but as a matter of fundamental law. Is there an unavoidable minimum energy price for processing a piece of information written into the bones of physics itself? And the answer he found is one of the most beautiful and underappreciated results in all of science, because it ties the abstract world of information directly to the oldest and most unbreakable law of physics, the second law of thermodynamics. Here is the idea, as plainly as I can put it. Imagine the smallest possible piece of information, a single bit, a 1 or a 0. Now imagine erasing it. You take that bit, whatever it was, and you force it to a known state, say you set it firmly to 0, wiping out whatever it used to be. That feels like it should cost nothing. You're just clearing a slot. But Landauer realized that erasing a bit is not nothing at all. Before you erased it, the bit could have been in one of two states, a 1 or a 0. After you erase it, it is definitely 0. You have reduced the number of possibilities. You have taken something uncertain and made it certain, and in doing so you have decreased the disorder, the entropy, of that tiny system. And the second law of thermodynamics has an ironclad rule about entropy. It cannot simply vanish. If you push entropy down in one place, it has to come out somewhere else. So when you erase that bit, the lost disorder has to be paid for, exported into the surrounding world as a tiny, unavoidable puff of heat. Landauer even calculated exactly how big that minimum puff of heat has to be. At room temperature, it comes out to about 3 times 10 to the negative 21st joules for every single bit you erase. That is a fantastically, almost unimaginably tiny amount of energy, a fraction of a fraction of a fraction of what it takes to warm a single drop of water. But it is not zero, and it is a flaw. It is the least you can possibly pay to erase one bit of information anywhere in the universe, and no amount of cleverness or better engineering can ever get you below it. Every thought a machine has ever had, every calculation, every erased bit has cost at least this much heat. Information, Landauer proved, is not some airy, weightless nothing. It is physical. A bit is a real thing, with a real, unavoidable thermodynamic cost. There is a detail hidden in that limit that becomes enormously important later, so let me plant it now. Landauer's flaw is not a fixed number, it scales with temperature. The colder you run your computer, the less heat each erased bit is forced to dissipate, and the closer to free your thinking becomes. Run your machine warm, and every bit costs more. Run it cold, close to the bitter cold of space, and the price of thought drops toward the theoretical minimum. Hold on to that, because when we finally imagine what an ultimate civilization would look like, this one fact, that cold is where thinking is cheapest, is going to shape the whole picture in a way you would never expect. And I want to be clear about how universal this flaw really is, because it is the reason any of this applies to aliens at all. Landauer's limit does not care what your computer is made of. It does not care whether you think with silicon, or with carbon, or with the folded proteins of a living brain, or with some exotic substance we have never dreamed of. It does not care whether you are human, or machine, or something a billion years more advanced than either. The limit comes not from engineering, but from the second law of thermodynamics, which is one of the deepest and most universal laws we know, governing everything from a cooling cup of coffee to the fate of the entire cosmos. Any mind, anywhere, on any world, running on any hardware, that erases information as it thinks, must pay this same minimum heat cost. It is not a human limit or a technological limit, it is a law of the universe, and that means the story we are telling about efficiency and heat, and the flaw beneath all thought, is not a story about our particular civilization. It is a story about every possible civilization there has ever been. For 50 years this was treated as a lovely piece of pure theory and nothing more, because real computers were so wildly, absurdly inefficient that Landauer's flaw was hopelessly far below anything a working machine came anywhere near. Our chips dissipated billions of times more heat per bit than Landauer's limit demanded. The fundamental flaw was a distant abstraction, like a speed limit of 1 trillion miles an hour on a road where the fastest car does 10. It proved a profound point about the physical nature of information, but the limit itself sat so far beneath any real device that it seemed like it would never actually come into play. But two things changed that. First, in 2012, a team of physicists in France and Germany finally measured the effect directly. They trapped a single microscopic particle in a tiny double-welled trap, erased one bit of information about which side it was on, and measured the heat that came out. And the heat dissipated, saturated at exactly Landauer's bound, precisely as predicted, half a century after he predicted it. The flaw was real. It was not just math. It was a genuine feature of the universe. Think about how remarkable that experiment is. A physicist in 1961, working with pencil and paper and pure reasoning about entropy and information, calculated the exact minimum heat that erasing a single bit must produce. He had no way to test it. The machines of his day were billions of times too crude to even approach the limit, and they would stay that way for decades. He simply trusted the logic, that information is physical and that the second law is unbreakable, and he wrote down a number. And 51 years later, when technology had finally grown delicate enough to measure the heat from erasing one bit in one microscopic trap, the universe returned exactly the number he had predicted. That is the kind of thing that should give you chills about physics. A chain of pure thought, reaching across half a century, landing precisely on reality. It tells us that this flaw is not a guess or an approximation. It is as real and as certain as the fact that heat flows from hot to cold. And it means that when we talk about the ultimate limit of computation for any civilization anywhere, we are not speculating. We are standing on one of the most solid pieces of physics we possess. And here is why that solidity matters so much for our story. Because it means the destination is fixed. Every computing civilization, no matter where it starts or what it is made of, is walking down the same road toward the same flaw, and that flaw is not negotiable. The question is never whether a civilization moves toward Landauer's limit. Given enough time, it must, because efficiency is what advancement is. The only question is what happens along the way, in the dangerous stretch of road between where we are now, billions of times above the floor and generating mountains of waste heat, and that distant cool destination where thinking is nearly free. That stretch of road, it turns out, is where civilizations live or die. And second, our machines have been racing toward that floor. As we have made our chips smaller and packed their transistors ever tighter, the waste heat they throw off has become the single greatest obstacle to making them faster. This is not a distant abstraction to you. It is the reason your phone gets warm in your hand. It is the reason your laptop needs a fan. Waste heat is now the enemy, the wall that every chip designer is fighting against, and that fight is pushing the whole industry, decade by decade, down toward Landauer's floor. We are still a few billion times above it, so there is a long way to go. But for the first time in history, the gap is closing, and it is closing along a curve that points, unmistakably, at Landauer's limit as the final destination of all computation everywhere. Not just our computation, any computation. The thinking of any mind on any world, made of any material at all, is bound by this same flaw, because it comes not from engineering, but from the second law of thermodynamics itself, which governs the entire cosmos without exception. There is something almost poetic in where this limit sits, and it is worth dwelling on for a breath before we move on. For most of the history of computing, heat was an afterthought, a nuisance, the reason machines needed fans and cooling. Nobody building the first computers thought of heat as fundamental. It was just an annoying byproduct, like the noise of an engine. But as our machines have grown more powerful and more tightly packed, heat has climbed from a nuisance to the central obstacle, the thing that ultimately limits how much thinking we can pack into a given space. And Landauer's insight tells us this was inevitable all along. Heat and information are not separate concerns that happen to collide. They are two faces of the same thing. To think is to organize information, and to organize information is, by the deepest law of physics, to produce heat. There is no way around it, no clever trick, no future technology that escapes it. The connection is woven into the fabric of the universe. Every mind that has ever existed, or ever will, anywhere, is a small engine turning energy into thought and shedding heat as it goes, and the efficiency of that engine has a hard ceiling that no one can exceed. That is not a limitation of our era. It is a feature of reality itself. So now we have the whole picture in place. We have a ladder that measures the wrong thing, raw watts, and breaks when you check it. We have a better ladder, efficiency, that measures how much thought you can extract from each joule. And we have the bottom of that better ladder, Landauer's limit, the hard physical floor of how efficient any mind can ever become. And with all three of those pieces on the table, we can finally ask the question this whole video has been building toward. If advancement really means efficiency, and if the ultimate destination is a civilization computing right at the edge of Landauer's limit, then what would such a civilization actually be like? What would it look like from across the light years? And the answer, once you see it, quietly detonates everything we thought we knew about how to find alien life. Part 7. What an advanced civilization really looks like. Here is where the whole picture turns inside out, and I want to walk into it slowly, because it is the moment the title of this video is about. In the old picture, the one we all grew up with, a truly advanced civilization is the one with the biggest fire. It builds a Dyson sphere. It blazes with the harvested light of its entire star. It is the most powerful, the most conspicuous, the most obvious thing in its corner of the galaxy. That is the Type 2 we were all taught to imagine. But look what happens when you switch rulers, from raw energy to efficiency. In the new picture, a true Type 2 civilization is not the one that builds a Dyson sphere and burns brightest. It is the one that has become so unbelievably efficient at processing information that it has pushed all the way down to Landauer's limit. It is a civilization whose thinking generates almost no waste heat at all. A civilization that can perform colossal, galaxy-spanning amounts of computation, whole inner universes of thought, while sipping only the faintest trickle of energy. In the old picture, advancement means a bigger fire. In the new picture, advancement means a fire so clean that it barely glows at all. And that single inversion, that one flip from power to efficiency, quietly destroys the entire assumption behind our search for alien life. Think about how we have actually been looking. For 60 years, we have searched for the waste. We built our whole strategy around finding the leftover heat of a busy civilization. We look for the excess infrared glow that a Dyson sphere would give off, the warmth radiating from a star wrapped in machinery. We listen for the spillover of powerful broadcasts. We hunt for the signature of a civilization burning a star's worth of energy, because we assumed that the most advanced civilizations would be the most wasteful, the hottest, the brightest, the loudest. We have been searching, in other words, for the smoke of an enormous fire. But a civilization sitting at Landauer's limit throws off almost no waste. It has stopped making smoke. It would be cool. It would be dim. Its thinking would be so efficient that it produces barely any excess heat for us to detect. From across the light years, such a civilization would be very nearly invisible. Not hiding, not cloaked, just quiet and cold and efficient in exactly the way that makes it impossible to see with instruments we built to look for heat and waste. Remember that detail I asked you to hold on to, the one about Landauer's floor scaling with temperature, the fact that thinking is cheapest when it is coldest. Now it comes back and it changes everything. Because a civilization that has truly grasped the physics of efficient thought would not seek out the bright, hot hearts of galaxies to build its mind. It would flee them. It would seek out the coldest, darkest, most remote corners of the universe it could find, the remote quiet places far from any star, because that is where computation costs the least, where each thought is nearly free. Picture that for a moment. Everything in our search assumed that advanced life would gather where the energy is, around blazing stars in the crowded galactic core. But if the goal is efficient thought, the smartest thing in the universe would do the opposite. It would go out into the cold and the dark on purpose, precisely to think more cheaply, and in doing so it would place itself exactly where no telescope would ever think to look. The most advanced mind in the cosmos might be sitting in the emptiest seeming void we can find, and we would have written that void off as nothing at all. And there is a second reason such a civilization would be invisible, beyond just running cold. It would have no reason to spread, to conquer, to sprawl across the sky in the way we always imagined. Colonizing star after star is thermodynamically expensive. It burns colossal amounts of energy to move mass across the enormous distances between stars, and a civilization optimized for efficiency has little reason to waste that energy, conquering territory it does not need. What would it gain? More room for what? If your civilization has turned inward, toward the depth and richness of its own thought, then a single cold, quiet, superbly efficient node could hold more experience, more life, more meaning than a whole sprawling galactic empire of the old wasteful kind. The mature civilization does not get bigger. It gets deeper. And a thing that is turning inward and growing quieter is the exact opposite of the loud, expanding, star-conquering empire we have spent a century scanning the skies to find. And this is not a hypothetical complaint about our methods. We really have built our searches around finding waste heat. Astronomers have run actual surveys scanning tens of thousands of galaxies, looking for the specific infrared signature that a civilization capturing large fractions of its star's energy would leave behind, the warm glow of a Dyson sphere or a whole galaxy studded with them. The logic was sound, given the old assumption. If advanced civilizations are enormous energy harvesters, they must dump enormous waste heat, and that heat should glow in the infrared where we can catch it. So we looked. We looked hard, across huge swathes of the sky, and we found nothing that we could confirm. No galaxy visibly being eaten by its own civilization, no star cleanly wrapped in warm machinery. For a long time, that null result was taken as just more evidence for the Great Silence, another way in which the universe stubbornly refuses to show us anyone. But look at what the efficiency reframing does to those searches. If advanced civilizations bend toward Landauer's flaw rather than toward bigger fires, then a survey hunting for waste heat is not a test of whether they exist. It is a test of whether they are wasteful. And the answer it keeps returning, that we see no great glowing engines, might not mean the galaxies are empty of minds. It might mean that any minds out there long ago stopped being wasteful, stopped glowing, stopped leaking the heat we know how to detect. Our most careful searches for alien civilization were designed to catch exactly the kind of civilization that the new picture says cannot exist for very long. We built a net to catch the smoke of a bonfire, and then concluded the forest was empty when we caught none, never considering that a mature civilization might have learned to burn without smoke at all. Do you feel what that does to the Fermi paradox? We may have been searching for precisely the wrong thing this entire time. We assumed the most advanced civilizations would be the most visible, the brightest engines in the sky, because we assumed advancement means power. But if advancement actually bends toward efficiency instead of raw power, then the most advanced civilizations would be the hardest ones to see, precisely because they have stopped wasting the energy we know how to detect. The galaxy could be full of them. It could be quietly humming with ancient, efficient minds, each one thinking at the very floor of what physics allows, throwing off no more heat than a cold rock, making no noise our telescopes are tuned to hear. And to every instrument we have ever built to search for the fires of civilization, all of them together would look like exactly what we see when we point our telescopes at the dark. They would look like empty space. This is the first genuinely disturbing turn the Fermi paradox takes in this story, and I want to say it as plainly as I can, because it upends an intuition almost everyone carries. Most of us quietly assume that if aliens were out there, and if they were truly advanced, we would surely have noticed by now. A civilization that powerful would be obvious. It would light up the sky. It could not possibly stay hidden. But this reasoning has it exactly backwards. The more advanced a civilization becomes, on the efficiency ladder, the quieter it may get. The more it matures, the less heat it wastes, the dimmer its signature, until the very mark of a supreme intelligence is not a blaze at all, but a kind of profound stillness. A silence we never once thought to look for, because we were busy scanning for the roar. There is a smaller, more human version of this same reversal, and it might help the cosmic one land. Think about how a person changes as they grow wiser over a lifetime. The young often mistake loudness for strength, mistake taking up space for mattering, mistake intensity for depth. And many people, as they age and deepen, grow quieter, not because they have less to say, but because they have less need to prove it. The deepest person in a room is rarely the loudest. Real mastery in almost any craft looks effortless and calm from the outside precisely because all the wasted motion has been trained away. The master chef makes fewer movements than the novice, not more. The master musician plays with less visible strain, not more. Efficiency and quiet are the signatures of things that have been perfected. So why would we expect a civilization to be any different? Why did we ever assume that the most advanced beings in the universe would be the ones making the most noise, burning the most fuel, taking up the most sky? That was the assumption of a young species, one that still equates greatness with loudness. A more mature intuition might have guessed all along that the truly advanced would be quiet, the way still water is quiet, the way real mastery is quiet. The silence that Fermi noticed on that walk to lunch 75 years ago might not be the silence of an empty universe. It might be the silence of a universe full of minds so efficient that they make no sound. We looked at the quiet sky and read it as absence. It might instead be the signature of maturity itself. The cosmos might be quiet for the same reason a library is quiet, not because no one is there, but because everyone who is there has grown up. Part 8. The Wall in Our Own Century. Now, if that were the whole story, it would be strange and a little beautiful and we could leave it there. But it is not the whole story, because there is a second cluster of recent papers, and they take this idea and sharpen it into something with a deadline, something that stops being about distant aliens and becomes very suddenly about us, about this decade, about the machines we are building right now. These studies look at what is happening to our own energy demand in the age of artificial intelligence, and they find that the old slow curves have snapped. For all of human history, our energy use crept upward gently, 1 or 2% a year, the modest climb Kardashev built his scale around. But the electricity demand of artificial intelligence, of the enormous data centers training and running these models, is not growing at 1 or 2%. It is growing at something closer to 15% a year. And a 15% annual growth rate is a monster. It is so steep that it decouples entirely from every economic trend that came before it. Our civilization's hunger, which grew like a slow tide for its whole existence, has suddenly begun to climb a cliff, driven by the machines we are building to think for us. If that pace holds, then by around the year 2050, the energy consumed by artificial intelligence alone could equal the energy consumed by the entire rest of the world combined. Everything else humanity does, all of it, matched by our thinking machines alone. And you do not have to take this on faith as some far-off projection, because you can already feel the leading edge of it in the world around you. The companies building these thinking machines are right now racing to construct data centers so hungry for power that they are reviving old nuclear plants and planning new ones just to feed them. Communities are watching their electricity grids strain under the load. The warmth pouring off these server farms is real, physical heat, enough that some of them are built beside rivers or in cold climates just to help carry the heat away. This is not a distant scenario dreamed up by theorists. It is happening in the present tense, in the news, in the infrastructure being poured this year. The papers simply take that curve, the one we can already see bending upward all around us, and ask what happens if it keeps going. And when you follow it forward honestly, it does not lead to a mild inconvenience. It leads to a wall. And this collides with a wall. Not a wall made of running out of fuel, a wall made of pure physics, built from the second law of thermodynamics, and the papers call it the Kelvin limit. Here is the trap, and it is a trap you cannot engineer your way out of, no matter how clever you are. Suppose we solve the energy problem completely. Suppose we invent a perfect, clean, effectively limitless source of power. Say we finally master nuclear fusion, and we can pull energy from seawater almost without end. You would think that solves everything, but it does not because of one merciless fact. The second law guarantees that every joule of energy we use, no matter how cleanly we make it, ends its life as waste heat. Energy does its work and then it becomes heat. Always. There are no exceptions. And that heat has to go somewhere. A planet can only shed heat in one way. It radiates it out into space, glowing faintly in the infrared. And there is a limit to how fast it can do that. If you keep generating more and more heat, the planet has to get hotter and hotter to radiate it all away fast enough. So run the arithmetic forward at that 15% growth rate, and the result is stark and strange. The problem is not that we run out of fuel. The problem is that we generate so much waste heat that the surface of the Earth is driven up toward the boiling point of water, 373 Kelvin, 100 degrees Celsius, in roughly 67 years. Even if we could fuse every atom of deuterium in every ocean on the planet, the sheer volume of the heat we would generate along the way would cook the world long before we ran out of fuel to burn. The oceans would boil, not because we lacked energy, but because we succeeded too well at using it. I want to make sure you catch how strange and how important this is, because it runs against everything we usually worry about. Almost every fear we have about energy is a fear of scarcity, of running out of oil, running out of coal, running out of uranium, and in this scenario those fears come true almost immediately. At 15% growth, the papers note, our conventional fuels, the fossil fuels and the uranium, get exhausted in about a decade, gone in 10 years. But here is the twist that makes this different from every ordinary energy crisis. Solving the scarcity problem does not save you. Suppose we do the miraculous thing. Suppose we crack nuclear fusion, the dream of limitless clean power, and we can pull energy from the deuterium in seawater in quantities that dwarf anything we have ever had. We would have effectively unlimited fuel, and it would not matter, because the wall was never really about fuel. The wall is about heat. Every joule of that limitless fusion energy still ends up, in the end, as waste heat that the planet has to shed. And so even with a perfect, endless, clean power source, the 15% curve still drives the surface of the Earth toward boiling in the same 67 years. This is a wall you cannot innovate your way through by finding more energy, because more energy is precisely the thing that builds the wall. It is the strangest kind of trap. The better you get at making power, the faster you cook. And that is the moment the whole framing snaps into focus. Because this is not just an abstract limit that some faraway alien civilization might one day face. This is a curve that starts in our own data centers this year. The heat is not metaphorical. It is the literal warmth pouring off the machines we're building right now to do our thinking for us. And the timescale is not cosmic. It is human, which means the great silence, the thing Fermi puzzled over, stops being a story about them and becomes a story about us. Let me take you up above the whole thing so you can see it the way physics sees it. Rise up, off the surface, until the entire Earth hangs below you as a single warm body, suspended in the enormous cold of space. Every light, every engine, every data center humming with artificial thought is a tiny ember on that body, and the planet sheds their combined warmth the only way it can, by glowing softly in infrared, radiating its heat away into the dark. For all of history, those embers were few enough that the Earth stayed comfortably cool, easily shedding what little heat we made. Now watch the embers begin to multiply, 15% more of them each year. The data centers spread across the continents like coral across a reef, the demand doubling and then doubling again and again. The planet tries to keep pace, glowing a little hotter to shed a little more heat, but heat radiates away slowly and the embers multiply fast, far too fast, and slowly, inexorably, the whole warm body of the world begins to heat up, not from the sun, not from any greenhouse gas, but simply from the raw thermodynamic exhaust of its own thinking. And somewhere along that curve the seas themselves begin to steam. I am not describing a distant science fiction nightmare. I am describing what happens if a single number, the 15%, simply keeps going. That curve plays out not over millennia, not over centuries, but inside a single human lifetime. 67 years. Sit with that number, because it is a very different kind of number than the quadrillion years we started with. 67 years is not a cosmic abstraction. It is within the lifetime of children who are alive today. It is a wall that our own civilization is walking toward, at a pace set by the very technology that is reshaping daily life this very year, in the news, in the headlines, in the machines quietly answering questions in millions of pockets right now. And this is the exact point where a distant question about aliens turns around and becomes a mirror held up to our own faces. Because the transition we are entering, this explosive growth of thinking machines, is not just an economic story or a technology story. It might be the most dangerous passage a civilization can attempt, and it might be, at long last, the real answer to why the sky is so silent. Part 9. The filter with a face. Put the two walls together, the efficiency floor at the bottom and the heat ceiling above it, and they point straight at one of the most haunting ideas in the entire search for alien life, an idea called the Great Filter. The Great Filter was proposed in the late 1990s by an economist named Robin Hanson, and it is a simple, chilling response to Fermi's silence. It goes like this. If the galaxy should be teeming with life but appears empty, then somewhere along the enormous road that leads from lifeless chemistry all the way up to a galaxy-spanning civilization, there must be at least one step so difficult, so improbable, that almost nothing ever makes it through. That step is the filter. It is a wall on the road that stops nearly everyone, and the terrifying question, the one that keeps the people who think about this up at night, is a single one. Where is the filter? Is it behind us, or is it ahead of us? If the filter is behind us, that is wonderful news. It would mean that the hard step, the near impossible hurdle, was something like the origin of life itself, or the leap from simple cells to complex ones, some ancient bottleneck that we have already, miraculously passed through. It would mean we are among the vanishingly rare survivors, and the road ahead is open. But if the filter is ahead of us, that is the worst news imaginable. It would mean there is some barrier waiting up the road, some wall that every civilization slams into right around the level of development we are now reaching and does not survive. It would mean the silence of the sky is the silence of a graveyard, full of the civilizations that came before us and hit the wall we are still driving toward. For a long time, the candidates for the Great Filter were the usual suspects, the catastrophes we could imagine happening to ourselves. Nuclear war, a killer plague, an asteroid strike, runaway climate change, a supervolcano. And all of these are real dangers, but they share a weakness as explanations for the universal silence. They are all a matter of chance. Some civilizations would get unlucky and die, but surely not all of them, not every single one across billions of worlds. A good Great Filter cannot be a roll of the dice that some survive. It has to be something that nearly every civilization runs into, almost by necessity, something built into the very process of becoming advanced. And that is a much harder thing to find. What could possibly trip up almost everyone, no matter how careful or how lucky they were? And what these new papers add is a specific physical candidate for a filter that lies just ahead of us, and it has exactly that quality of near inevitability. The transition a civilization has to make, from burning fuel wastefully to mastering information efficiently, from the slow Kardashev climb to the blistering Karnak climb, may be a narrow and deadly bottleneck. Because look at what we just saw. If you reach for explosive computational growth too fast, before you have learned to do it efficiently, before you have driven your machines down toward Landauer's floor, you slam into the Kelvin limit, and you cook your own planet in decades. The very act of becoming a thinking, computing, information-rich civilization generates a tidal wave of waste heat, and if your growth outruns your efficiency, that heat kills you. There is a cruel elegance to how this works, and it is worth spelling out slowly. The danger is not that a civilization is careless or greedy or foolish. The danger is baked into the very shape of intelligence itself. To become advanced is to compute more. To compute more is to generate more heat, by the iron law of Landau and the second law of thermodynamics. And if your ability to compute grows faster than your ability to become efficient, if your appetite outruns your cleverness even for a few decades, the heat catches up with you and cooks your world. The trap is not laid by an enemy. It is laid by your own success, by the very thing that made you advanced in the first place. And every civilization, no matter how wise or careful, has to walk through this same door, because computation is what an advanced civilization does. You cannot skip it. You cannot go around it. The only question is whether you cross the gap between appetite and efficiency fast enough and cleanly enough to come out the other side. That is what makes it such a good candidate for a universal filter. It is not a stroke of bad luck that only some suffer. It is a structural feature of the road that every traveller must cross. This is a filter with an actual mechanism, and that is what makes it so much more unsettling than the vague versions. It is not triggered by a war or an asteroid or a nearby exploding star, some external catastrophe you could blame on bad luck. It is triggered by success. It is triggered by a civilization becoming clever enough to build machines that think, and then feeding those machines faster than its world can shed the heat they produce. The filter is not a disaster that happens to you. It is a trap you build for yourself, out of your own intelligence, out of your own ambition, at the exact moment you start to become truly powerful. And if this is the filter, if this is the wall on the road, then it explains the great silence with brutal economical clarity. The sky is quiet because the step we are taking right now, this decade, the artificial intelligence step, the leap into explosive computational growth, is the step that most civilizations do not survive. And notice how it reframes the very idea of danger. We usually imagine that the threats to a civilization are things that go wrong, a weapon misused, a disease unleashed, a system that fails. We picture catastrophe as a kind of breakdown, a failure of competence or care. But the filter these papers describe is not a breakdown at all. It is what happens when everything goes right. A civilization that is doing brilliantly, inventing thinking machines, growing its intelligence, expanding what it can compute, is precisely the civilization that walks fastest toward the wall. Success is the accelerant. The better you are at the thing that makes you advanced, the faster you approach the danger. There is no villain in this story, no mistake to point to, no moment where someone should have known better. There is only a civilization becoming more of what it is, more intelligent, more capable, more hungry for computation, and finding that the road of its own triumph runs straight into a wall of its own heat. That is a far stranger and more sobering kind of danger than any weapon, because you cannot avoid it by being careful or wise or good. You can only avoid it by becoming efficient fast enough, by learning to think without burning before the heat catches up. Think about what that means. The headlines you read about the soaring energy appetite of data centers, the warnings about power grids straining under the load of artificial intelligence, the debates about how much electricity a single query consumes. We tend to file all of that under ordinary news, under economics and policy and infrastructure. But these papers are suggesting something far larger is hiding inside those headlines. They are suggesting that we may be watching, in real time, in our own newspapers, the approach to the great filter. That the answer to the oldest question in the sky, the reason the universe looks empty, might be getting written right now, this year, by our own hands, in the server farms spreading across the Earth. The filter is not some far future technology or some distant cosmic threat. It might be the thing we are building this decade, and whether we pass through it or die against it is, as far as anyone can tell, still undecided. Part 10. 2 Ways to Disappear. Here is something I want you to notice about this new answer to the Fermi paradox, because it is the feature that makes it so unusually complete and so unusually strange. It does not give us one explanation for the silence. It gives us 2, and they are perfect mirror images of each other. 2 opposite fates, and yet both of them lead to exactly the same empty sky. In the first fate, the transition kills you. A civilization reaches our stage, builds its thinking machines, and races up the computational curve faster than it can learn to be efficient. It slams into the Kelvin limit, it floods its own world with waste heat, and it burns out, a bright brief flare of intelligence that overheats its planet and goes dark before it ever manages to spread to the stars, before it ever builds anything a neighbor could see, before its signals ever reach anyone. It is a candle that flares up and gutters out in an eye blink of cosmic time, and from across the light years, nobody ever knew it was there at all. It rose, it thought, it cooked itself, and it vanished, all in a window too short and too quiet for the universe to notice. In the second fate, the transition succeeds, but success itself makes you invisible. A civilization threads the needle. It grows its intelligence and its efficiency in step, carefully, and it survives the bottleneck. It learns to compute at the very edge of Landauer's limit, doing more and more thinking with less and less waste, until it settles into a cool, efficient, nearly heatless existence. A silent processor of unimaginable amounts of information, sitting at the thermodynamic floor, throwing off almost no signature at all. It does not burn out. It grows up, and in growing up, it grows quiet, until it too disappears from every instrument we know how to build. Look at what that gives us. Two completely opposite outcomes. In one, intelligence destroys itself. In the other, intelligence perfects itself. And yet, crucially, from where we sit on Earth, with our telescopes tuned to search for waste heat and radio noise and the smoke of enormous fires, both outcomes look identical. Both produce silence. Let me sit inside that second fate for a moment, the monastery rather than the graveyard, because it is the more beautiful of the two and the harder one to picture. Imagine a civilization that made it, that grew up. It did not conquer the galaxy, because it never needed to. It did not wrap its star in machinery and blaze across the sky, because that would have been the wasteful adolescent thing to do, and it grew out of that phase long ago. Instead, it turned inward and downward and colder, pouring its unimaginable resources not into bigger engines but into richer and deeper thought, running enormous inner worlds on a whisper of power, in some quiet dark place we would glance past without a second look. From the outside there is nothing to see, no megastructure, no beacon, no sprawling empire of light, just a patch of cold space that our instruments would file under empty. And inside that patch, more life, more experience, more meaning than 1,000 blazing empires of the old kind. That is not a civilization hiding from us. It is a civilization that has simply become the kind of thing our tools cannot perceive, the way a radio tuned to one station cannot hear a conversation happening in the next room. It is right there. We just do not have the ears. And if both fates, the ash and the garden, produce the same silent sky, then something humbling follows. We cannot tell, just by looking, whether the universe around us is a graveyard or a monastery. We cannot tell whether the darkness is full of the dead or full of the wise. We have been staring into that darkness for 75 years, reading it as one simple thing, absence, when it may be a rich and layered mixture we never learned to distinguish. Some of that silence, the ashes of the ones who reached exactly where we are now and did not make it through, and some of it, the profound stillness of the ones who did. Either the advanced civilizations are gone, burned to ash in the transition, or they are still here but so quiet and so cool that we cannot tell them from empty space. Either the filter is a wall that destroys, or it is a door that leads somewhere we simply cannot observe. And in both readings we look out at the galaxy, and we see nothing, and we call it empty. I find it worth pausing on just how unusual it is for a single idea to explain a mystery from both directions at once. Most theories are fragile in a very specific way. They make one prediction, and if that prediction fails, the theory falls. But this efficiency framework has a strange robustness to it, because it does not depend on which of the two fates is more common. Suppose you learn tomorrow that most civilizations burn out in the transition. The framework would explain the silence. Suppose instead you learned that most civilizations survive and grow quiet. The framework would explain the silence just as well. Suppose the truth is a mix, some burning, some transcending. Still the same silent sky. There are very few answers to Fermi's question that remain standing no matter how the details shake out, and that is either a sign that the idea is capturing something profound, or a warning that it is slippery enough to explain anything, which is a criticism worth keeping in mind. But at the very least, it means the core insight does not rest on a single fragile guess about alien psychology or alien politics. It rests on physics, on heat and information, and the second law, the same everywhere, for everyone. And physics, unlike psychology, does not change its mind from one civilization to the next. Whatever strange forms of life and thought are out there, they are all bound by the same thermodynamics we are. That shared cage is exactly why the same explanation can reach every one of them at once. This is what makes the idea so complete and honestly so haunting. Most answers to the Fermi paradox have to explain away every single advanced civilization in the same way. They all died, or they are all deliberately hiding, or they never existed in the first place. The explanation has to be uniform, and that always feels a little forced because why would every civilization in a galaxy of billions of stars make the same choice or meet the same end? But this framework does not need uniformity at all. It allows a galaxy where some civilizations burned out in the transition and others passed through it into invisibility, a real mixture, and it predicts the exact same silent sky from both. The universe could contain, side by side, the ashes of the ones who failed and the quiet gardens of the ones who succeeded, graveyards and monasteries scattered through the dark, and from Earth, with the eyes we currently have, both the graveyards and the monasteries look the same. They look like nothing. They look like the silence we have been staring into for 75 years, reading it, all this time, as simple absence. But it might not be absence at all. It might be a mixture we have never learned to read. Some of that silence might be the quiet of the dead, civilizations that reached exactly where we are now and did not make it through. And some of that silence might be the quiet of the wise, civilizations that made it through and grew so efficient that stillness is simply what they became. We have been treating the darkness as an empty page. It might be a page covered in writing, in an ink our instruments cannot see. This mixture, this idea of graveyards and monasteries scattered together through the same silent dark, also quietly answers one of the strongest objections people raise against every solution to the Fermi paradox. The objection goes like this. Any explanation for the silence has to account for every advanced civilization, and it is hard to believe that billions of independent civilizations, spread across billions of years and billions of worlds, would all make the exact same choice or meet the exact same fate. Surely at least one would be different. At least one would spread loudly, or broadcast deliberately, or blaze across the sky in the old way. A uniform answer always feels a little too tidy, a little too convenient. But the efficiency framework does not need everyone to do the same thing. It allows for a galaxy of radically different outcomes. Some civilizations grew too fast and burned out. Others grew carefully and passed through into quiet efficiency. Perhaps a rare few even did spread in the old blazing way, briefly, before the physics caught up with them too. The framework does not demand a single story. It only points out that the two most likely stories, catastrophe and transcendence, both end in silence from our point of view, and so a genuinely diverse galaxy, full of civilizations that each chose their own path, could still present us with exactly the empty-looking sky we see. It is the rare answer to Fermi that does not require everyone to be the same, and there is, buried in the darker reading, a strange and genuine consolation. Because if some civilizations pass through the filter into quiet efficiency rather than dying against it, then the silence is not proof that intelligence always destroys itself. It leaves the door open, just barely, that surviving the transition is possible, that some do make it, and it tells us something almost gentle about what waits on the far side if we get there. The reward for surviving is not a blazing empire stamped across the stars. It is not conquest, not domination, not a galaxy set on fire with our ambition. The reward for surviving is something much quieter and much deeper. A profound, invisible stillness. A civilization that has stopped needing to shout because it has learned to think instead. Which of these two futures humanity is walking toward, the graveyard or the monastery, is a question these papers cannot answer for us. But they make one thing unavoidably clear. We are walking toward one of them, and we are walking toward it now. Part 11. The Other Doors. Now, I have been leading you down a single path for a while, and it is a compelling one, and I believe it is worth taking seriously. But I would be doing you a disservice if I let you walk out of tonight thinking this is settled, or proven, or the final word. It is not. These are new papers. They are speculative reinterpretations, offered as proposals, not delivered as facts. The underlying physics they lean on, the Kardashev scale, the second law of thermodynamics, Landauer's limit, all of that is rock solid. But the specific models built on top of it, the Carnac unit, the 67-year timeline, the whole efficiency filter idea, those are fresh, and they compete with other answers that are just as serious and in some cases a great deal simpler. So let me be honest with you and open some of the other doors, because a true picture has to include the ways this idea could be wrong. The first door is the oldest and the most sober, and it is this. Maybe the silence needs no exotic filter at all, because the numbers were never as generous as they sound. There is a widely discussed analysis from a few years ago that took the famous Drake equation, the formula that tries to estimate how many communicating civilizations are out there by multiplying together the rate of star formation, the fraction of stars with planets, the odds of life, the odds of intelligence, and so on, and it did something the optimistic versions rarely do. It accounted honestly for how enormous the uncertainties are in each of those terms, and when you do that carefully, a startling possibility emerges. There is a substantial chance that we are simply alone. That intelligent life is so rare that one civilization per galaxy, or even one per many galaxies, is exactly what we should expect to find. On this view, the silence is not disturbing at all. It is not a filter ahead of us, or a graveyard around us. It is just the quiet of a universe in which the hard step, the origin of life, or the leap to complex cells, or the birth of intelligence, was so improbable that it happened only once here, and it lies safely behind us. We should give that its full weight. The efficiency filter idea is a fascinating new possibility, but it has to stand next to the plainer possibility that there was simply never anyone out there to hear. It is worth pausing on how strange it would be, emotionally, if that turned out to be the answer, if we really are alone. We have spent this whole video imagining a galaxy full of quiet, efficient minds, or full of the ashes of the ones who failed. But the plainest possibility is that there is no one at all, and never was, anywhere within reach. And that is its own kind of vertigo, in some ways a heavier one. It would mean that the Earth is not one candle among many in a dark room, but the only candle, and that everything we call life and thought and love is a fragile local accident that happened once, and might happen nowhere else. It would place an almost unbearable weight on us, because it would mean that if we go out, the light does not simply pass to another. It ends. This possibility deserves its full weight, not because it is cheerful, but because it is honest, and because it changes what is at stake in the very transition these papers describe. If we are one civilization among billions, then our fate is a data point. If we are the only one, then our fate is everything. The second door pushes back on the timeline itself, and this one matters because the 67-year boiling scenario is the most alarming number in the whole story. That number depends entirely on the 15% annual growth rate of artificial intelligence continuing, unbroken, for decades. And here is the thing about explosive growth rates. They almost never continue unbroken. They bend, they saturate, they collapse. A curve that's steep is usually a curve in the early frantic part of its life, before something, economics, or physics, or simple limits, reaches in and flattens it. The artificial intelligence energy boom could level off as the technology matures, as efficiency gains finally outpace demand, as the easy growth gets used up. And notice that even the authors of these papers frame the runaway curves as a warning of what happens if present trends simply continue, not as a prediction that they will. A civilization might pass through this whole information transition gently, spreading it over centuries instead of decades, cooling its computation with clean energy managed carefully, and never come anywhere near the Kelvin limit. In that reading, the transition is real, but it is not a filter. It is just another hurdle that a careful civilization steps over without ever breaking stride. The wall is real physics, but whether any given civilization actually hits it depends on choices, and choices are not the same as thermodynamic laws. And the third door questions the most poetic part of the whole idea, the claim that an ultra-efficient civilization would be invisible. Is that even true? Even a supremely efficient civilization still has to radiate the waste heat it does produce, however small. A very large one, spread across many worlds or many structures, might still be spotted by the faint infrared glow of its cold computing if we knew to look for that instead of for the roar of a Dyson sphere. Or it might choose to send deliberate signals, or it might build things we simply have not thought to look for yet. The absence of the specific signature we happen to search for, the waste heat, the narrowband radio, is not the same as true invisibility. The history of the search for alien life is full of moments where we said we have not detected it, and what we really meant was we have not yet learned the right way to look. So the efficient and silent hypothesis might be less a story about civilizations that cannot be seen, and more a story about a channel we have not yet learned to tune into. It may not be that they are invisible. It may simply be that we have been listening on the wrong frequency all along, and honestly, that reframing might be the most useful thing this whole idea gives us, whether or not the darker parts turn out to be true. Because for 75 years, the search for alien life has been guided by a single quiet assumption, that advanced civilizations would be big and bright and wasteful, and so we pointed our instruments at the sky expecting to find fires. This new picture, even if it is only half right, tells us that assumption might have been aiming us in exactly the wrong direction. It suggests we should be looking not for the hottest things, but for the coldest, not for the brightest, but for the dimmest, not for sprawling engines, but for compact, quiet, efficient ones. It suggests that the interesting places to search might be the cold, empty voids we have always dismissed as empty, rather than the blazing galactic cores we have always assumed life would gather in. Whether or not any given civilization boils itself or transcends itself, this reframing hands the search for alien intelligence a genuinely new map, and tells us we may have spent decades searching the wrong half of it. Sometimes the most important thing a new idea does is not to answer the old question, but to tell you that you have been asking it while facing the wrong way. And there is a fourth caution worth naming, one that applies to the whole grand story rather than any single piece of it. This entire chain of reasoning rests on a set of very recent papers built on a brand new unit of measurement, using a cryptocurrency network as a stand-in for the computation of an entire species. That is a bold and clever chain of logic, and it may well be pointing at something true, but it is a chain, and every link is an assumption. The choice to measure a civilization's efficiency by Bitcoin's hash rate is inspired, but it is one particular window onto computation, not the whole of it. The projection of a 14 orders of magnitude efficiency gain is real for the narrow thing it measures, but stretching it into a universal law of civilizations is a leap. Good science offers ideas like this precisely so that other scientists can test them, argue with them, and either strengthen them or tear them down. So hold this whole picture the way its own authors do, as a fascinating proposal that reframes an old question in a new and productive way, not as a proven map of the cosmos. Its greatest value may not be that it is right, but that it gives us, for the first time, a way to reason about civilizational survival in the hard language of physics, rather than the soft language of guesswork. I lay these doors out not to knock down the idea I've spent this whole video building, but because the idea is stronger, not weaker, for standing next to its rivals. The disturbing thing the Fermi paradox may have revealed is not a proven doom. It is a genuinely new and serious possibility, one that has earned a place in the conversation next to We Are Alone, and the growth will bend, and maybe they are not so hidden after all. Which of these is true, we do not know. We may not know for a very long time. But there is one of these possibilities that implicates us directly, that puts the answer not in the distant stars but in our own hands, in our own century, and it is to that one, the mirror, that I want to return as we come to the end. Part 12. The Mirror in the Silence. Strip away the specific models, the ones that are new and speculative and will be argued over by scientists for years to come, and something real and permanent is left standing underneath, something deeper than any single paper, and it is this: does intelligence, anywhere in the universe, tend to survive its own success? Because look at what every version of this story has in common. Every civilization that reaches the level of building thinking machines seems to arrive, sooner or later, at the same narrow gate. It is the moment when its hunger for computation begins to outrun its world's ability to shed the heat that computation makes. And on one side of that gate lies collapse, a bright brief flare that overheats its planet and goes dark before anyone across the light years could ever have known it was there. And on the other side of that gate lies transformation, a civilization that learns to think at the very floor of what physics allows, and in doing so becomes so cool, so quiet, so efficient, that it disappears from every search we know how to run. We do not know which side of that gate is more common. We do not know which fate the universe hands out more often, and here is the part that should stop you where you stand. We do not even know yet which side we ourselves are walking toward. So the true revelation of the Fermi paradox in this telling is not a fact about aliens at all. It is a mirror. The silence of the sky may be trying to tell us something about ourselves. It may be telling us that the step we're taking right now, this decade, the rush to build machines that think, faster and faster, growing hotter and hungrier by the year, is the exact step that decides the fate of every civilization that ever takes it. That the great filter is not behind us and not some distant threat waiting 1,000,000 years up the road, but here, now, in the choices being made this very year about how fast and how carelessly we build. Maybe the universe is silent because that gate is deadly, and most who reach it do not pass through. Or maybe it is silent because those who do pass through grow so efficient and so still that quiet is simply what wisdom looks like from the outside. Either way, we are the ones standing at the gate now. There is one more piece to fit into place before we close, and it ties this whole story back to the oldest tool we have for thinking about alien life. Back in 1961, the same Frank Drake who first pointed a dish at the stars wrote down an equation, a way to estimate how many communicating civilizations might be out there. It is a chain of factors multiplied together, the rate at which stars form, the fraction with planets, the odds that life begins, the odds it becomes intelligent, and so on down the line. And at the very end of that chain sits one last term, a letter L, which stands for the average length of time a communicating civilization survives. Every other term in the equation has been narrowed down by decades of astronomy. We have gotten better and better at counting planets, at estimating the odds of habitable worlds. But L has barely budged, because it depends on the one thing we have no data on at all, whether civilizations like ours tend to be long-lived and stable, or whether they tend to arise and then quickly snuff themselves out. L is the great question mark, and whether the galaxy is crowded or empty depends, more than on any other single factor, on the value of L. And do you see where this whole story has been quietly heading? The efficiency framework, the transition through the gate, the wall of waste heat, all of it is really an attempt to reason about L. To ask, in the hard language of thermodynamics rather than the soft language of hope, whether a civilization can survive the passage between the heat ceiling and the efficiency floor. It suggests that L might not be governed by politics or luck or wisdom at all, but by physics, by whether a species learns to think efficiently before its own growth overheats its world. That is a startling thought. It means the survival of a civilization, and the answer to why the sky is silent might come down to the same thermodynamic knife edge. And it is worth remembering that the symbolic clock we keep for our own species, the doomsday clock, currently sits at 85 seconds to midnight, the closest it has ever been. These papers are suggesting in effect that one of the hands on that clock is thermodynamic, that the question of our survival and the question of the great silence may turn out to be the very same question. And that is the sense in which we were wrong. The 3 words on the thumbnail. We were wrong about what we were looking for. For 60 years we searched the sky for the biggest fires. We assumed that greatness meant power, that the most advanced beings in the cosmos would be the ones burning brightest, wrapping their stars in machinery, blazing across the dark so unmistakably that we could not possibly miss them. And the answer these papers hand us quietly is that the most advanced thing in the universe, the thing we ourselves might one day become if we survive the next 100 years, makes almost no fire at all. It is not the loudest thing in the sky. It is the quietest, not the brightest, the coolest. We were looking for a roar, and the signature of a grown-up civilization may be a kind of silence we never thought to honor. And notice how completely this rewrites the story we usually tell ourselves about the great silence. The gloomiest version of the Fermi paradox says the silence means death, that intelligence is a suicide machine, that everyone destroys themselves and so will we. But this framework does not force that darkness on us. It offers a second reading in the very same breath. Yes, some die in the transition, but some pass through, and the reason we do not hear from those is not that they perished. It is that they grew quiet in the way that only something truly advanced can. The silence in that reading is not a warning that intelligence always ends. It is, if anything, evidence that some intelligences endure and that endurance simply does not look the way we expected. It does not shout. It does not sprawl. It settles into a stillness we mistook for emptiness. There is room in this idea for hope, real hope, but it is a strange and grown-up kind of hope, one that asks us to let go of the childhood dream of a galaxy on fire with our glory and accept instead that the mark of a civilization that made it might be indistinguishable, to young eyes like ours, from an empty patch of sky. And maybe that is the most quietly radical idea in this whole story. We have always measured greatness by how much noise a thing makes in the universe, how much space it takes up, how brightly it burns, how far its influence spreads. Our myths of advanced civilizations are myths of conquest and expansion and blazing power, empires among the stars. But what if that whole image is backwards? What if the truest sign of a civilization's maturity is not how loudly it announces itself, but how gently it learns to exist? What if growing up for a species means the same thing? It often means for a person, learning that you do not have to be the loudest thing in the room, that depth matters more than noise, that the richest life is often the quietest one. A civilization that has learned to think without wrecking its world, to grow without burning, to become enormous on the inside while staying small and cool on the outside, would look like nothing to us. And it might be the most successful thing the universe has ever produced. We have been mistaking silence for failure. It might be the sound of everyone who succeeded. There is something almost humbling in that, and I want to leave you sitting with it as the night goes quiet around you. We spent so long imagining our future as an ever larger fire, a civilization of endless growth and endless power, spreading and burning and conquering the stars. And it may be that maturity looks nothing like that. It may be that the civilizations who make it through are the ones who learn, in time, that the point was never the size of the fire, that growing up means learning to do more with less, to think without burning your world down, to become quiet not because you have failed, but because you have finally understood. The reward for surviving the gate may not be an empire. It may be a stillness so complete it looks, from the outside, exactly like an empty sky. Somewhere out there, above the roof over your head, past the thin blue edge of the atmosphere, the universe has already run this experiment countless times. On countless worlds, intelligence has arisen and reached this same gate and either flared out or fallen silent. The sky above you right now holds the answer. It has held it all along. Every point of a light you can see, and all the darkness between them, is the universe having already voted on whether minds like ours survive what we are about to attempt. We just have not yet learned how to read the silence. But we are learning, and the most important thing we have learned tonight is that the silence was never empty. It was never the absence of an answer. It was the answer, written in a language of stillness and cold and efficiency, that we are only now, a century into asking the question, beginning to understand. What actually happens when a civilization grows up? Look up. The sky has already told us. We're finally starting to listen.